Hello, everyone. Welcome to today's lecture at MLSS 2021 Taipei. I'm the host of this lecture. My name is Shou-De Lin. I'm an assistant professor at National Taiwan University. Today, we are very honored to invite Professor Shou-De Lin to join us. Shou-De is a professor in the Department of Computer Science and Information Engineering at National Taiwan University. And he is also now the chief machine learning scientist of AINTU-REN, a very well-known AI company in Taiwan. And Shou-De has more than 20 years of experience in artificial intelligence, machine learning, and natural language processing. During his time at NTU, Shou-De has received several Best Paper Awards at international conferences. He is the recipient of several prestigious research awards, including FAO's Young Scholar Innovation Award and the Most Wudayo Award. He has collaborated with more than 50 companies and has won the 2007 Google Research Awards, the Microsoft Research Awards for 3 times, and the IBM Research Awards. He is also the all-time winner of the ACM KDD Cup, for which he has led or co-led the NTU team to win 7 championships. After joining AINTU-REN, Shou-De has led the IDEAL team to win the best overall AI-based analytics solution in the 2020 AI Breakthrough Awards. And today he will be sharing some tips on what you should do when your machine learning model doesn't work well. Yeah, so welcome, Shou-De. Yeah, and the time's yours.
Thank you. So thanks, Sandra, for the introduction. So actually, it's my second opportunity to talk in MLSS. And so as I hint last time in today's lecture, I'm going to talk about some more practical issues in terms of how can we train a machine learning model and how can we boost the performance of it. And my name is Shou-De Lin. Okay. So today's talk will be based on my hands-on experience in solving real-world ML tasks, and that includes our experience in participating KDD Cup, and also my past experience in helping more than 50 companies in solving their machine learning tasks. Also, some of the experience when I worked in Microsoft Research as a visiting scholar. Finally, my hands-on experience in AINTU-REN since 2020. Okay, and so I will just briefly highlight what we have done in the past KDD Cups. And I think Professor Shou-De Lin was one of the members for a couple of years. So it's so KDD Cup was a well-known competition for machine learning, and so every year there will be different hosts and there are different challenges. Like for example, in 2008 we are trying to solve impedance data problem, and in 2009 it's how to handle heterogeneous data, and so on and so forth. And so the team actually were formed by every year we have different set of students, and they try to do their best to win the competition. And fortunately, we did pretty well on several of the tasks. And so some of the experience I'm going to share definitely come from those experience we have obtained through competitions. Okay. So we know that machine learning models are evolving very fast. Okay, so it's now and then, so we see a lot of papers published every day on daily basis, and they usually outperform the previous ones. And so talk about 5 or 10 years ago, people were talking about SVM Bayesian network, but right now it's all about deep neural network. Okay, And we also realized that the state-of-the-art models today are likely to be infamous after 5 years because new things are coming out every single second. So it's so in terms of teaching or in terms of knowledge transferring, it's very challenging because we kind of don't know which will last and which will not. So while preparing for this talk, I'm thinking about these particular questions. Are there some ideas about training machine learning model that can and should last longer? So people, whoever actually attend this lecture, will still find the knowledge sharing in this lecture be useful after 5 or even 10 years. So instead of talking about all kinds of fancy state-of-the-art machine learning model, here I like to share something that's probably, I believe, will probably last longer and probably still be useful in several years. And so how did I choose which idea I should share to satisfy this criteria? So my selection criteria is very simple. I went back to see what we have learned in the past 10 years, and I select some of them that seems to be still valid at this moment. So if there's something that has been working for say 2010 until now, then they are likely to be still working in 5 to 10 years. So that's what I really want to share in this particular lecture. Oh, by the way, so if you have any questions, so feel free to just type in the chat box, and there will be a midpoint break, and I will answer some of them during the break, and then finally I will answer the rest of the question when the lecture ends. Okay. So then I will, of course, I like to start with ML 101. So what's machine learning? And everything starts from here. So machine learning tries to optimize a performance criterion using example data or past experience. And so I believe you should be very familiar with this. So from mathematical point of view, we are given some data X, and we want to learn a function that map X to Y. And this fx function is what everybody tries to optimize in the machine learning task. And of course, the fx can perform several different types of tasks. If fx maps S into a label Y, we call it a classification. And if it maps to a numerical number, we call it a regression. And so we can use fx to map X to a set of Y in X, or a set of similar instances in the data set. It's called clustering. And we can also map this instance into a probability distribution, P of X. So it's called distribution estimation. So depending on what kind of purpose this fx serves, we actually can derive different types of machine learning tasks from it. But nevertheless, the ultimate goal is to obtain high quality fx given certain objective and evaluation function. And then I will move into the main thing of this talk, which is to discuss why machine learning models fail, meaning like what we can do if the prediction accuracy or whatever metrics is not satisfiable. Okay. So I will start with this machine learning diagnosis tree. So I believe when you found that the results of your machine learning model is not satisfiable, and you can go through this diagnosis tree and to figure out what could potentially be the problem. And I will start with, is this really machine learning task? Okay, so first we really want to ask is it correct we model this test as a machine learning task? Are you sure machine learning is the best solution for this task? So meaning to do machine learning or not to do machine learning? That's the key question. So I will list some of the common mistakes people might encounter when falsely model a problem into a machine learning problem. First, if this X, the input feature or input data, comes from a closed set with limited variation, so then it's probably not that suitable for a machine learning because we can simply memorize all possible X-Y mappings. For example, in this word translation using dictionary, so we can always memorizing what kinds of translation for this individual word should lead to. And so there's no need to build a sophisticated machine learning model for this. And if you do that, it probably won't get a satisfiable result as simple memorization. So on the right-hand side, so it's a simple tic-tac-toe task. So given there is not so many grids in this particular task, the best way is also to just memorize some key movement and follow that. You don't have to use sophisticated reinforcement learning to learn from this the practical data in this toe example. And the second is if fx can be easily derived by writing rules, then we probably just try to find out what kind of rules is the best suitable instead of building a data-driven solution. For example, for compression and decompression, in particular the lossless compression, so there is a specific algorithm we can compress this particular information without and there's another set of decoding algorithm, we can decompress it. And so for that, unless it's probably much easier, we can just simply follow those compression and decompression rules to do decoder and encoder instead of trying to use a sophisticated, for example, recurrent neural network to do that. So those cases are probably too easy or not suitable, not data driven for a machine learning task. And then we talk about if X is sort of independent of Y. So we already know that. So the given information is probably not that relevant to our target. So for example, if we are given the ID of a person, the name of a person, the wealth of a person, we are trying to predict the height of that person. So of course we can build a machine learning model for it. But if in the very beginning, we already know that there are the correlation seems to be not very strong, then it's expected, as expected, the results won't be too well. And our FX is not smooth, meaning that if we realize one of the tasks have this particular scenario, like if we give a small disturbance, would disturb X by delta X, that's a very small disturbance, then the Y, the particular output would receive a very dramatic change, meaning that this equation doesn't hold. Then that probably is not a very suitable problem for machine learning. Okay, so it's we either need really sophisticated nonlinear algorithm to model that, or it's probably not. We won't succeed in model that using machine learning. Okay. And finally, if there's no enough data to be learned, and later on I will talk about how to check that, and if we don't have enough X or enough instances to be trained, then machine learning model might not be as useful as we expected. Okay. Okay, so next question is like going down in this diagonal tree. So if I have decided this task is really ML solvable, but still couldn't get a good result. So what to do next? So let me see. Before I answer this question, I like to highlight there are several different machine learning scenarios, and we have to first decide which scenario this particular test belongs to before we try to apply any particular machine learning solution for it. So these different scenarios just like different kind of toolboxes. Okay, there are hammers, there are screwdrivers, and there are all kinds of different boxes of tools. And we have to first pick the right box of tools, and then we pick a specific tool out of it. So if it turns out this test is about hammering a nail into a wall, but you choose the box of a screwdriver, then is no matter which screwdriver is picking up for the next step, it won't get you very good results. Okay, so to do that, we probably have to first understand what kinds of a scenario a machine learning test can handle. So I will use probably 10 minutes to talk about understand what machine learning can do. So there are a lot of different scenarios a machine learning model can handle, and I will go through them one by one. And first, probably most people already know that in your summer school, I believe a lot of people talk about supervised learning. Okay, and supervised learning, as we can see that it's given a set of inputs and output pairs, and we are trying to learn the relationship between this input X and output Y. Okay, so there are two kinds of outputs. So it can be either categorical, we call it a classification problem, and it can be a real value, we call it a regression problem. Okay, so for example, we can take sensor information into account as input, and we are trying to predict whether this particular sensor is broken or not. Or we can take a lyric of song as input, and we are trying to predict whether this is a happy song or a sad song, or surprising or angry one. Or we can take, for example, the weather, traffic, air condition as input and try to predict the PM 2.5 value of today's PM 2.5 value, and that's called regression problem. Okay. And so I will probably just dive deeper to talk about some particular tasks people normally use for supervised learning. So besides the very typical classification and regression task, and there are a lot of solutions proposed for this multi-level learning. So in multi-level learning, this X, the input are used to predict a set of output labels instead of just one single label. Okay, so in this example, we have 3 different labels, and we want to predict. And of course, those labels, they are correlated. They are not completely independent. So we know that their prediction probably should be, to some extent, related to each other. So we want to do a joint prediction as a whole instead of predict each label one by one. So this is called multi-level learning, and there are a lot of solutions proposed for that: binary relevance, label power set, MLKN, IBLR, and a lot of new solutions in deep neural network. And so there's a lot of applications for multi-level learning. For example, this image tagging. So in image tagging, we are not just provide one single tag for each image, because this image can contain a lot of different concepts. So in this case, this beach boy image can be taken as 60s classic rock, pop, and surf, and so on and so forth. So it's really a multi-level learning problem. And also, like one of the tasks that's slightly, it's also a supervised test, but slightly different from the previous one. It's called multi-instance learning. So this is in particular very popular in medical data analysis. Okay, so it's a supervised learning task, but the goal is to predict the label of a bag of instances instead of one single instances. But during the training, we are provided the individual label for each instance. Okay, so how do we decide the label for the bag? So the particular rule is that a bag is considered as positive if at least one of the instances inside the bag is positive. For example, let me check on the, see if I can show, sorry. For example, on the right-hand side, this positive bag contains one positive instance and 4 negative ones. And a bag has to be assigned a negative label only if all the labels, all the instances are labeled negative. Okay. So why I just said it's very common in medical, so because we are treating, so we can probably treat each label or each instance as one of the X-ray image. Okay, so say if a particular person, this person takes a lot of X-ray image, but if one of them is considered as unhealthy, so or probably contains some cancer cells, then this particular person will be labeled as not healthy. Okay, so to label this particular person as healthy, we need all the images to be negative. And so, and eventually we are learning this bag label model. So we are trying to optimize the accuracy among those bags, not individual instances. And cause-sensitive learning is also another variation of a supervised learning. And I believe Professor Shou-De Lin has talked about this previously. And so it's all about assign different penalties to different kind of mistakes in the model. And we have a lot of different algorithms that can take consider this penalty matrix to optimize the model. Okay, and so one of the very useful application scenario for cause-sensitive learning is for fraud detection. So in fraud detection, for example, credit card fraud, assigning this a target as fraud is much, if missing, I mean like mistakenly assign a fraud case as a normal case probably costs much more than mistakenly assign a normal case as fraud case, because a lot of money could be lost. Okay, so in this case, we probably want to consider cause-sensitive learning. And there are also, besides supervised learning, there are other types of machine learning tasks that probably people have developed different set of solutions for that. For example, semi-supervised learning, and it's probably, based on my own experience, it's probably the most used scenario for industrial, because in many cases, when we are trying to solve a machine learning task in a company, so the label data is usually very sparse. There are some, but not a lot. And So semi-supervised learning are considering this type of a scenario that assuming very, very few instances are labeled and a lot of them are not labeled. But we want to take advantage of those unlabeled data to build a better model. So that's what this semi-supervised learning does. So this is a very intuitive example. So say if we have very few training example, this blue circle dots and these green triangles on the right-hand side. So with only a small set of training examples, there are a lot of different decision boundaries that can clearly separate these two sets of instances. In this case, both red lines, red dotted lines and black dotted lines could potentially be a suitable decision boundary. But when we consider those unlabeled instances as the figure shown on the right-hand side, we can realize that probably this red line is better than this black line, because if you choose this black line, then some of the unlabeled data might get incorrect label. So people normally we have this concept of clustering. We kind of tend to cluster unlabeled points closer to the labeled one and closer to the one with the same, and we assign the label to the unlabeled points based on the nearest labeled instance. So this is a basic idea why semi-supervised learning could potentially be useful. And of course, there's another set of learning model we call unsupervised learning scenarios. So it's more like learning without teachers. It's also very popular for real world usage. And so we are obtaining a lot of data, X, and that's it. So we don't have particular thing about the target Y. Either we don't know what we are going to predict, or we know, but we don't have label data for that. Okay, and so with a bunch of instances X, there are still a lot of things we can do through unsupervised learning. So it's normally we call learning what happens in general. Okay, so think about how babies learn their first language. So where like so starting from the first day of the baby, they are their parents or other relatives, they start talk to the baby, but they are not teaching those baby how to speak language. They just simply use their own language to communicate with the baby. So there's no specific teacher tell this baby what is correct and what is not. But by dumping a lot of like vocabulary or sentences to this baby, eventually after several years, the babies learn how to speak that language. So what inside the baby's mind is to try to figure out what normally happens and what normally does not happen, and eventually they can output things that happen very frequently. And but as opposed to the study of the second language. So when we were at school, we normally have to study our second language. And in this case, normally, usually there's a teacher that tells us the grammar, that tells us what is the right thing to do and what is not the right thing to do in terms of this particular language, and we learn from that. So that's more like a supervised learning, okay? So in this unsupervised learning, we are given a bunch of input X, and that's it. Okay, so what can we do from this a bunch of input X? There are a lot of things. For example, we can estimate P of X. So from this particular training set X, we can try to understand what kind of X has higher probability, or what kind of unseen X has higher probability or lower probability. So that's called estimation, distribution estimation. And so if people have ever encountered Bayesian-based solution, is try to estimate the core is to estimate the joint probability distributions of instances. Or we can try to find association between different instances. For example, if a particular instance X1 occurs, what's the probability another instance or another feature X2 occurs? So this X could be instance, could be features, could be a set of instances, or could be a set of features. And so in this test, we are trying to find dependency between inputs. So they can be translated to association rule mining, causality analysis, and those models are trying to find this connection between either features or instances, or we can find the similarity between different instances, and that's called clustering. So the key spirit of clustering is to group similar things together, okay, and separate different things into different groups. Okay, so given a bunch of input X, there are a lot of things we can still do and to perform analysis, and that's called unsupervised learning. And of course, people, I think in the previous lecture, you have encountered this particular learning test called reinforcement learning. So it's in particular useful for consecutive decision making. So if you have a series of decisions and one decision can affect another, and you are trying to optimize a particular objective, reinforcement learning might be the best solution for that kind of scenario. For example, playing games. So in this example, you have this Super Mario game to the AI is like to play this Super Mario game. So in the very beginning, it knows nothing about the game. So it can do try and error, and so try to learn under which state or which situation, which button or which actions should be picked for optimizing the rewards. So after a lot of rounds of try and error, so the reinforcement learning allows us to learn what's the best action one should pick at a particular situation to optimize the reward. Okay, so I believe people know AlphaGo, so it's the DeepMind's AI algorithm that's based human in 2 years ago. Okay, so in AlphaGo, it's a combination of supervised learning and reinforcement learning. So there are 2 stages. So in the first stage, the multi-class classification is applied. So it's training from the previous experts' data. So learning from what those experts did in a particular situation. So we map this fx as the action or which position this AI should, what's the next move. And the result would be that after learning from those experts, people are doing very well in Go. AI can really outperform normal players, but not the best ones. That's why it needs the second stage to further improve itself. So it's from playing with the AlphaGo playing with itself through reinforcement learning. Okay, so through playing with itself, it further can refine or polish its policy to outperform the human beings. So the reward will be eventually if this game is won by AI and the action is still the next move. So based on whether it wins or not, and this reward will feedback back to the previous moves, and so you will try to refine its policy to optimize this process. So this called so AlphaGo is not just learning from human. There's another stage, is learning from playing with itself. Okay, so in the past 10 minutes, I briefly introduced different scenarios, and there are a lot of, so I just sample some key scenarios. There are, of course, others. Feel free to dig deeper. But with that, then we can answer this question: have we found a correct scenario for this task we are trying to solve? Okay, have we identified this correct toolbox to be used for the problem? I will show several case studies, and so to further elaborate this idea. For example, if you are facing a sequence labeling tasks, for example, like speech recognition, you have this a series of waveform, and we are trying to recognize it, and so output a series of characters or words. For OCR, we are giving a bunch of so for example, image, a text in image, and we are trying to recognize it. All kinds of different tagging problems. So we are given a sequence, and for each individual element in this sequence, we want to give it a label. So it's called sequential labeling task. And there are a lot of ways we can solve this, depending on, for example, how much data do you have? How many training label are available? Okay. So if there's sufficient amount of training label, we probably can model it as simple multi-class classification problem, meaning that for each individual word or individual instance in this sequence, we do an independent prediction what it should be labeled. Or we can sample it as a sequential labeling. There are sequential labeling algorithms to do that. For example, conditional random field, HM, recurrent neural network. So those algorithms, they consider this assignment or this labeling test as dependent, meaning that each single instance, the result of each single instance can affect the prediction of the other instances. So by jointly consider this, it's possible to obtain a better result. But we probably will, it could be the case that if there are too few training instances, this model might not be as effective, or there could be like you need much more extra efforts to tune up the parameters in the model. And or if there are some scenario people don't have enough training labels or even no training labels, there are also unsupervised learning tests. Unsupervised learning problem models proposed for this problem. For example, like EM algorithms, it can be operated in an unsupervised manner, meaning that I don't need a training example tell us which label has been assigned to each individual instance. But still, there are we can, by estimating the joint distribution and by iteratively updating this posterior distribution as well as the observation, the probability of the observation, we can still find a local optimal solution for this particular task. The second case study is click-through rate prediction. So click-through rate is a very common metrics for advertisement. Okay, and so it's actually measured given a particular user. If I show you this particular advertisement, what's the likelihood you will click on it? Okay, so it's really a ratio. Okay, and so at the first glance, it looks like a regression task. Okay, so we are trying to predict a probability whether this user will click on this advertisement. But depending on the training data and depending on the usage scenario, we might not might or might not want to model it as a regression task. So in fact, CTR itself is number of click divided by number of views. So meaning that if there are 2 users, the first user we show this user 1 10 different advertisement, and assuming it click on 5 of them, so the CTR of this user is 0.5. But for another user, user 2, if we show 1,000 different advertisement to it, and this user to click on 500 of it, it still yields 0.5 CTR ratio, but statistically that's very different. It's one is 5 out of 10, and the other is 500 out of 1,000. So whether to model this as classification or regression depends on what kind of eventual evaluation metrics we really care about. For example, if we really care about user level CTR accuracy, meaning that each user is equally important, regardless of whether this user has been shown a lot of times or much fewer times, and their CTR is, we consider the CTR as equally important, then we probably can treat this as a regression problem, means that 0.5 for user 1 is equivalent to 0.2 for user 2. But for many online companies, we really care about the click level CTR instead of the user level CTR, meaning that we care about each individual click, how accurate we can predict each individual click. Then we should transfer this into a binary classification problem, meaning that if we are showing to the user 10 times, then 10 different instances are generated. And for the other user 2, assuming there are 1,000 showing, then we have to produce 1,000 training instances for this. And in this case, we can optimize this click level CTR. And there's another case study. Let's assuming we are handling these temporal value prediction tasks. On the left-hand side, there are several different time series. Okay, and so we are trying to predict what will happen next. For example, we can treat this as a stock market prediction. And the black one is a US stock market, and the green one might be a stock market in Taiwan, and the yellow one might be stock market in Japan. So each country, and there is a different stock market time series over there. But we are trying to predict what will happen in the next day. Okay, so what kind of task should we model it, and what kind of machine learning models should we apply to solve it? And so I think the most intuitive trivial solution would be a regression problem. Okay, so we treat it as a regression problem, and we first concatenate all sequences into one. Okay, so if there are 10 time series, and we just concatenate all that into one time series, and we can predict what will happen in the next. And or we can treat it as an online learning problem. Okay, online learning problem, assuming data are coming incrementally, and the model are updated once the new data comes in. Okay, so the good things to model this as an online learning problem is we can always use the most recent data and to make prediction instead of a training incrementally. I mean, we can incrementally update the model, and we can probably consider recent data. We can offer higher weights to those recent data, and we can probably build a more sustainable model through it. Or we can consider it as a multi-task learning problem. So it's less intuitive, so I will use a figure to show that. So in fact, we can treat this, for example, 10 different time series as 10 different tasks. Okay, so in each time series there's X, meaning what happened previously, and there's Y. That's what we are trying to predict for the next day. Okay, and so for each of the predictions, so we are predicting T different actions or T different labels, and for each of them we can use all kinds of previous time series. It's not necessarily limited to its own time series. We can always use the time series from the other country. For example, for stock market, we know that those stock market, they are kind of correlated in different countries. So while trying to predict, for example, the stock price for US market, we probably want to consider those stock market in Asia or in Europe. So in this case, everybody can contribute to the prediction of the other time series. And so this can be a model as a multi-task machine learning task. So multi-task learning, meaning that we jointly train different tasks, but we allow them to affect each other. Okay. So let's see, how much time do I have? Let me quickly answer. How many questions are there? 2. Okay, so I will probably take 5 minutes. Let me see. Oh, there are only 2 questions here. I can quickly answer them, and then we will take a 5-minute break. So first question, what if we don't know the rule of fx in P11? It's difficult enough to use ML. Let's go back to page 11. Let me elaborate. So as I said, so it's if we know the rules, then it's probably better to use those rules. But if we don't know the rule of fx, of course, then machine learning could be useful here. In particular, if those rules they are sophisticated ones, and we want to use some nonlinear functions to approximate it. So I believe in previous lectures, you probably learned that deep neural network can approximate a lot of sophisticated nonlinear functions, and if the rules is not known, and of course machine learning could be a possible rescue. And let's see what's next. In P11, why the function is not smooth will lead to ML model to fail. The smooth criteria since somehow suggests ML model should be linear functions. Yeah, so this is a nice one. So on smooth function here, so of course, if we already know this function is very unsmooth, then I will not suggest using machine learning. But in many cases, we don't know. So if we don't know, then it's of course worth a try. And so it really depends on, as you mentioned, this delta x. What's this delta x represents? So if we realize that, so there's a good way to check it. For each instance, so how small this delta x should be to determine whether a machine learning model is useful or not. For each instance x, try to find its nearest neighbor. Okay, so this is called nearest neighbor classification. So say if for a lot of cases, this nearest neighbor has different label as this particular instance, then this test is probably too hard for machine learning, meaning that even your neighbors is not very similar to you. But of course, it depends on what kind of similarity function you are using to find these neighbors. But in general, if their features look very similar, but their results looks very different, then it's questionable for machine learning. But of course, we know that right nowadays there are a lot of powerful models, in particular deep learning models. They can estimate or they can approximate this dramatic change of things, but still, like, it's all about the degree of difficulty. Right? So if this smoothness is very sharp, unsmoothness is very serious, then it's very likely ML won't do a very good job. Okay. AlphaZero is one of the best chess engines which defeated Toadfish, but how did they achieve that by using RL when school also use RL? So I'm not quite sure what Stockfish really does, but AlphaZero tries to so it's based on reinforcement learning, and from scratch, none of the human knowledge is used. So it's basically, if there is a good way to confine a search space and to find a suboptimal solution inside this reinforcement learning framework, it's possible to eliminate the necessity of using human labeling data. But it's usually only effective for limited domain tasks like games. Okay, so for chess or for video games, it's very different from real world tasks, because in those games, the search space is still very constrained comparing with the real world task. So that means like the action space, the search space for action, for action planet is quite limited. So it's possible like to enumerate a lot of choices within a small amount of time. So that's why reinforcement learning is considered as very useful for games, but less effective comparing to another set of machine learning tests for real world case. Yeah. Okay, so I think I probably answered whatever I have right now, and I will take a 5-minute break, and we will be back soon. Thank you. Okay. So let's keep going. So next, if you have identified an ideal ML scenario, but the model still doesn't work, what will happen? So I'm going through this particular part here. First, once we determine the scenario, the next step is to choose a proper machine learning model inside this scenario. So, for example, if it's a supervised classification, there are still a lot of classification algorithms one can choose from, like support vector machine, neural network, or decision tree and random forest, so on and so forth. And so here are some rule of thumbs how one can choose a proper model. First, we consider the size of the data. So if we don't have enough data, let's suppose small data, and we tend to choose linear model or simple model. For large set of data, it doesn't mean a linear model is not good. So we should probably try both linear and nonlinear model. And also depends on the sparsity of the data. If data is sparse, means more tricks. We need there are tricks to perform better and faster. Okay, and for if the data is dense, and we probably requires light algorithm that consumes less memory. And also we consider the balance condition of data. So if the label is imbalanced, meaning that the portion of positive and negative is varies a lot, then we usually need special treatment for minority class. For example, we can upsampling those minority class or assign a higher weight for it. And also the quality of the data. So, for example, if there are noise, missing values, and later on I will talk about some solutions for dealing with loss, but we have to be aware that some loss functions, for example, 0-1 loss or L2 are more robust to noise than others. For example, hinge loss or exponential loss. So along the way, there are several decisions you have to make in order to decide the best model for this particular task. And then you want to ask, do you have enough data to train the given model? And so a common way we check whether we have enough data is by drawing this learning curve. Okay, so in this learning curve, the x-axis represents the size of the data, and the y-axis represents the training accuracy. Okay, so if the training accuracy actually saturates, okay, and so with the size of the data, that means adding more data will probably not be very useful for training. Of course, we can also check testing, because then testing allows us to check overfitting, as I will mention later on. But if if you find that data size, once we grow the size of the data, the performance, in particular the training error, reduce significantly, we probably can try more data. Okay. So what should I do if I have a lot of data but they are not labeled? So this is probably by far the most common question I have been asked. And my honest answer is to try to get at least some of them labeled, because still, if you don't, you still need those for validation. Some of the label data for validation, even you are trying unsupervised learning algorithms. And so in several cases, if labels are too costly, and we can resort to semi-supervised solutions, as I described previously, or transfer learning solutions. Okay. Transfer learning, or some people call it domain adaptation, is one of the very useful set of solutions when dealing with lack of training labels in data. Okay, so the basic idea is that if for a particular domain there is not enough data to train the model, then we seek for another domain that we already have some label data. But because these are two different domains, it's very dangerous to directly apply label data from the other domain to this domain. So there are a lot of different assumptions for transfer learning. They can extract knowledge from this source domain and use those knowledge inject to the target domain to improve the performance of the target task. Okay, so there I'm showing you two of the examples, and those are already been shown by many people, could be useful. For example, we are trying to build an image recognition model for airplanes, but we don't have enough training data for airplanes. But instead, we have a lot of training data for birds. Okay, so then we can use those data for birds to build certain model and transfer those knowledge to this airplane domain to boost the performance of an airplane model. Second example, so I want to build a recommendation system for a company. R1, for example, is sales books, but I only obtain rating data or customer data from another company, R2. It can sell books or movies or whatever. And so there are ways to transfer what we have learned from company R2 to improve the performance of a recommender system for company R1. Okay. Then I mentioned we can check the learning curve for training data, but that doesn't tell us how can we determine if a model is too complicated for a particular task. So we normally call it overfitting. Okay, overfitting is one of the probably most notorious enemy for machine learning. A lot of times we cannot obtain very good results in practical usage because of overfitting. And so how can we avoid overfitting? So it's really a very, very serious challenge questions. Here I provide several high-level guidelines and people can follow. First, Occam's razor. So Occam's razor tells us simpler model first. So whenever you are trying to solve a test using machine learning, I will recommend starting from a simple model. And so the reason to start from a simple model is that simple model tells us a benchmark result. And simple model is less likely to overfit because it's too simple, it's less complicated, it has higher chance to underfit than overfit. So and we record the training error, the validation error, and the testing error. So by recording training, validation, and testing accuracy, then for any further model, they are more complicated than this simple model. We can always check if it's overfitting. Okay. So this on the right-hand side, we can check this very useful diagram to check whether overfitting occurs. So when we increase the training iterations, normally the training error goes down gradually. Okay, and ideally it will probably goes to 0 if you have enough feature to feed the data. But it doesn't mean that the testing error will also have the same trend. And so normally testing error looks like this. It will go down to a very bottom, and then it will go up. And when it goes up, meaning it probably indicates that overfitting occurs. And so this is a technique called early stop or early termination. And by checking this training and testing error, we can determine when we should stop training the model to avoid overfitting. Okay. And also adding regulation to your model is a good and you should do to avoid overfitting. So regulation is a way to constrain the complexity of the model, and it allows you to avoid overfit the data. And also you need to consider quality of the data. So always train with high quality data, meaning that we want to make sure the features we are using have some potential to be useful for prediction. Okay, and so for example, user ID. Okay, so if we are trying to predict some of the demographic features, demographic behaviors of a user, and should we use user ID? And if the ID is assigned randomly in a system, then it's probably less informative to predict, for example, the gender for the user. And by knowing that, but if we are included into as one of the features into the machine learning model, it could be the case like by chance, the model just learns that a very sophisticated model just learns that using this user ID, it's much easier to overfit the data, the training data to get a very high quality result. The model will tend to ignore the other useful features and focus mainly on this user ID. Okay, so the quality of the feature can also affect how serious the overfitting can happen. So that's also this to the last part. So we need to remove some of the features, probably through feature selection, and if they tend to generate overfitting results. Okay, and next, I'd like to talk about the quality of data. Okay. So the quality of data first, we want to check data very noisy, okay? Noisy in terms of labels, okay? So by checking the labeling process, it's probably, we get some hint whether those labels, how accurate are those labels. A typical machine learning process looks like this, and there are, in the very beginning, we have the data labeled. Then we use the label data to train the model, and then we ship the model for real world usage. The humans are involved in this early stage of data labeling normally. Okay, but if one realize like this labeling could contain noise, then we probably want to refine this process into the following one. Okay, so in the very beginning, we need to clean the data, and we probably try our best to avoid ambiguity in the labeling process. And so then we bring the data for labeling. So at this stage, we want to make sure those data that are labeled by humans has higher chance to be accurate. But if they are not, then after model training, we probably can use those trained model to do what we call label refinement. So for example, one intuitive way to do that is to obtain those instances that model incorrectly assigned label back to the humans again to ask them to recheck whether those labeling are incorrect, because those are labels our model believes otherwise. Okay, so with this label refinement process, we have better chance to go back to retrain the model and to get a better one. Okay, so there should be a cycle going back and using this refined label to retrain the model. And so normally, if the data is made very noisy, then the human probably would be involved in this loop to optimize the training process. Next, does data contain many missing features? Okay, so whenever you obtain the training data, first check how many features are missing, or what's the percentage of missing ratio. Okay, a lot of the share of algorithm, if you don't do that, they will automatically fill in 0 or mean for the missing features. But if it turns out the missing ratio is very high, then you probably want to do something smarter than filling 0 or mean. And there are already a lot of research in this direction trying to provide solutions for missing features. And we can divide them into 2 different groups. The first set of solutions, they're trying to fill in the missing value and before performing learning. Okay, so to do that, we need to first determine what kind of missing scenario this particular data belongs to. So there's missing completely at random, missing not at random, and missing at random. And popular solutions are mice, and that has been there for a long time. And in recent years, there are some deep learning-based solutions like MIS-GAME. And the second set of solutions, and there are fewer of them, but they try to perform missing data imputation and learning at the same time. So for example, XRGAME and GREP, those frameworks, they provide you a way to jointly perform imputation and learning. So mostly they are based on deep learning models. Okay, so I've checked the data and avoided overfitting, but my model still perform poorly. So if that happens, what should we do now? Okay, then we have to look into the features. Okay. So the first thing you want to ask is, have you identified all the key features for this particular task? And this always usually involves domain knowledge and human judgment to determine whether there are features they are still missing but could potentially be useful. But here I like to provide a rule of thumb. And when generate the training data for machine learning, if you don't know a particular feature is useful or not, then you probably should try it, to include it and let the machine learning model determine whether they are useful or not. So when generating this data, if we have very high confidence this feature is useful or not useful, then we remove the features that are not useful, and we include those are either useful or we don't know. But there is a condition for this rule of thumb, is that we are given this data is sufficient. If the data, I mean, in terms of the number of training instances is not sufficient, then having a lot of features can lead to overfitting. So I believe in your previous lectures, people probably have already talked about these trainings, the relationship between the number of instances and the number of features. And so but what to do if the amount of training data is limited, then I would suggest it's better to trust human judgment to only include useful features. Then feature engineering. Okay, feature engineering turns out to be one of the best strategy to improve the performance. And based on our previous experience, usually it's very useful, but it can, but doing it incorrectly can also lead to catastrophe. So the goal is to explicitly reveal information, important information to the model, and we can either use domain information, domain knowledge, or we don't. And there are different ways to encode features, and there are also ways to combine features to do this feature engineering, which I will elaborate next. First, we want to check what kinds of features we have right now. So normally we can treat feature as two different categories. One is categorical feature, the other is numerical features, and then require different ways to encode for a machine learning model to be effective. For categorical features, we usually have to encode it to numerical ones. For numerical features, we have to consider scaling. Okay, so normalization or log or linear scaling, so on and so forth. I will talk about encoding categorical feature first. Okay. So encode, and those categorical features can all further be divided into two different types. The first is called nominal features, and the second one is called ordinal features. So I will start with ordinal features, easier. So ordinal features means those features are ordered. So they do have their semantic as gradually increasing or gradually decreasing. Okay, so for ordinal features, usually we can do ordinal encoding. So since it's gradually increasing or decreasing, so we can assign a numerical or integer number to each of them. For example, easy as 1, medium as 2, hard as 3. And for nominal features, meaning there's no order for the values or for the element of this particular feature, then there are two different ways to encode them. The first is to encode without label information. We encode those features without considering its label. And the most popular is probably people already know, it's what called one-hot encoding. So we expand this feature into a lot of binary features. Each binary code represents one feature value. We can do frequency encoding. So meaning that we replace each feature value by its appearing frequency. Okay, so then we have to first, based on the whole data set, to count how frequent each individual feature value is, and use that frequency as the encoding. Alternatively, we can encode nominal categorical feature using label information. And be aware that every time when we try to use label information in the feature encoding, we have to be aware that it can cause overfitting because we have considered labels here. Okay. But there are two popular ways to do this. First, it's called mean encoding. Mean encoding tries to encode the ratio of being positive for each feature value. So for this particular feature value, we assign the ratio of this value being positive in the label. Or we can do probability ratio encoding. So instead of using this P of 1 as the ratio of being positive, we can use this odd number, P of 1 divided by P of 0. So it's how likely this particular feature is positive divided by how likely it's negative. So those are different types of encoding for nominal categorical features. And nowadays, people are very familiar with deep neural network. They have proposed ways to encode categorical features use embeddings. Okay, so categorical features with large set of values can be very tricky. Okay, so here is a example in recommendation. Say we have a lot of users, and each user they have their favorite movie. Okay? But we know that there are a lot of movies, hundreds of thousands of movies there. So if we want to one hard encode this favorite movie, then it can be very sparse and the size can be very large. So we need tens of thousands or even hundreds of thousands of one-hot features to do that. Okay, and they would need to sparse large sparse matrix. And so people were thinking about maybe we can, instead of using large sparse matrix, we can probably encode this kind of categorical feature, use a dense vector which limited size. So this is called neural network embedding based solution. Okay, so I will use a typical so this is a figure to show how generally people do this. So assuming we have a bunch of categorical features and a bunch of numerical features, for each categorical feature, we can start from one high encoding of it, but then we pass it into a neural network of hidden layers, and you will eventually generate a dense output, but much comparing to the one high encoding feature, it will be dense, but the number of features can be shrink to a smaller size. Then we concatenate with the continuous numerical features, and then we start training the model. And the good thing for this kind of infra or this kind of framework is that the encoding can be trained together with the eventual classification task, meaning that this is the end-to-end training. The encoding itself can consider the learning task. So while trying to maximizing the objective of the learner, the encoding or the feature encoding can also contribute. So normally, if you have enough data, this could be a better better way to do encoding. And for numerical features, we need to do scaling normally. Okay, there are several commonly used scaling techniques. For example, the normalization, meaning that we minus the mean divided by max minus mean. Okay, so when should we use normalization and as opposed standardization? Standardization here is x, each feature minus its mean divided by its standard deviation. Okay, so there are still subtle difference between normalization and standardization. So one rule of thumb to determine which one to pick is you can check first whether this particular feature follows near Gaussian distribution or not. If a distribution is very similar to Gaussian, then we'll probably use standardization. And if this distribution is far from Gaussian, then normalization is a better choice. And normalization usually benefits neural network-based model, and because it makes training faster and prevents local optimal. And standardization are more robust to outliers. So if you found that this particular feature have a lot of outliers, meaning their values are very different from the others, then standardization could be more suitable. And there are also other scaling means, such as logarithmic, like log x plus 1. And this is particularly useful for large data values. And if you don't do log, then this particular feature will lead to very small weights. That makes the further interpretation much more challenging. And next, we can consider combining features. Okay, so why do we want to combine different features for feature engineering? And because we want to explicitly tell the model those combinations are useful. And depending on the complexity of the model, some models might be able to figure out those combinations itself, but others might not. But if we already know that by combining those features, they should yield very informative information to the model, then we can do that manually. So that's why we do feature combination. And so this is a good way to inject human knowledge into the model. For example, if your feature has some hierarchical relationship between each other, it will be very hard for a model to learn those hierarchical information between features. But by combining features into new ones, you will explicitly tell the model how those hierarchy can be integrated together to learn the model. Okay, so feature multiplication, feature division, and they are useful techniques one can try. And also, the second reason is like sometimes, in particular for industrial usage, sometimes linear model is preferred or it's used with whatever reason. And if this is the case, it's further important to automatically generate combination of features to tell this linear model they should be considered, because they are not as powerful as the linear model to identify those dependency between features. Okay, and popular solutions include polynomial mapping, and we can also or we can consider bigram, trigram features. Okay, but we have to be aware that the feature combination usually leads to large set of expansion on feature size. If we do polynomial mapping, meaning that you have this polynomial 2, at least polynomial 2 number of new features comes into the model. So it can lead to overfitting, and it can hurt the efficiency of the training. Also, in some of the cases, we realize that there's a trick. Using nearby instances, features from nearby instances are sometimes helpful. Okay. So meaning that instead of only use the features of this particular instance, sometimes we want to add some of the features of its neighbors. Of course, how do we determine the neighbors? That's another question. But we can use k-nearest neighbor, or we can use instance closing time, or instances closing space. So human knowledge is usually involved in determining what should be considered as neighbors, but those neighbor features are sometimes very useful in learning a model. So this is just showcase a result experience we learned in KD Cup 2010. And we realized that every time we add a set of new features into play, the error goes down. Okay, so by adding basic feature, we have this root square error. By adding, for example, combination features, by adding temporal features, by adding more combinations, and every time, like we train with more features and or more combination of them, we can yield a better model. Next, if everything else have already checked and the model still is questionable, then I like to suggest looking for the phenomenon called concept drift. Concept drift could be a cause for failure models. So what is concept drift? So it tells us over time, the context of the data or the relationship between features and labels has changed. So once those relationships changed, it means like the previous model trained on previous data probably not as effective. So this is a intuitive figure. So in a lot of the real world applications, people have observed this kind of behavior for the model. If you train the model and the model sit there to serve the customers, and usually it will happen like with the growth of the time, the model performance will go down. Okay, so the longer the model is used, the less effective it is. There are a lot of reasons. One possible reason is concept drift, and another reason is what people call serving sampling bias. So let me briefly introduce what kind of drift we should be aware of. Okay, so let's consider this joint probability of data. So assuming we have x, y, x means the features, y means the labels, and in a lot of machine learning model, we are trying to estimate this probability of x, y, the joint probability. And of course, it can be decomposed into the source, the x probability, and this channel probability means given x, what's the prediction of y, okay? And the first type of drift is called covariate drift, meaning that in this mathematic form, the p of x changes over time, but the p y given x remains the same. Okay, so I think we can use this figure to show this concept. So in the very beginning, we have this circle and triangle, and they are separated by this dotted line. But at the next time, the data have some drift, meaning that the new data comes in, their p of x changes. Although this decision boundary remains the same, but we are seeing this new black data comes in. That looks very different from the previous data we trained our model. So a suitable a model that considered concept drift should still yield good results, even this distribution of x changes. A more challenge task of concept drift is called actual drift. This assumes that the distribution of x remains the same through time, but the decision boundary changes. Is p y given x at this time 0 is different from this p y given x in time 1. So using this figure to illustrate, we can realize that at the next, in the very beginning, it looks like the white circle and white triangle. In the next timestamp, the black ones comes in. The black circle and black triangle follows the original distribution of x, but this decision boundary moves a little bit from the original one to this new one, okay? In the real world application, usually both px and py of x can change through time. So this is most difficult scenario, meaning that at the next timestamp, not only x, p of x changes, py of x also changes. So then the algorithm has to either react fast to this changing or be robust enough. The original model should already consider this kind of drift. So if a particular model doesn't really take those into consideration, then when the drifts happens, the performance of the model will go down seriously. For the sake of time, I won't be able to introduce the details of the solutions for concept drift, but here is a good survey paper. If you have interest, feel free to check them. And those are effective solutions for concept drift. So it can be divided into different dimensions. First, when should we consider drift and what kind of solution we should apply. So one type of solutions is called trigger-based. So it divided this concept drift into two stages. The first stage, we try to detect the occurrence of concept drift. Once it's detected, then we impose a solution to it. And the evolving means like we trying to, we are not detecting the occurrence of concept drift. Instead, we assume the concept drift has always been there, and we want to make sure the model is robust enough to consider a good solution for it. Okay, so it's called adaptive ensembles. And there are a lot of different means to deal with that. As in real world scenario, this really happens a lot. And if you in the future you have encountered this scenario that you have to build a model to serve your customer in the long run, not just for once, but for a longer period of time, you probably should consider how to handle this. Okay. So next, I'll talk about the machine learning model doesn't work well in real world scenario. So then it will refer to the very right hand side of a diagonal tree. The first you want to ask is the objective of your machine learning model align well with the ultimate application target. Okay, so this happens a lot. The model doesn't work well because you are training on a diverse objective comparing to the ultimate goal. Okay, so I'm showing you several examples. For example, in digital advertisement, your customer normally cares about the purchase, how your recommendation model can generate, can be effective in generating new purchasing. But because purchasing records are harder to obtain, or their labels are not as sufficient as other labels like click, view, or put in cart. So in many cases, we are training our model using the other labels, like those labels in the upper funnel, because they are more abundant than the purchase label. But it doesn't imply that increasing click or view or in cart will definitely increase purchase. So because of this gap, a model training on the previous stage of the purchase might not lead to satisfiable results if eventually purchasing is verified, is used as the eventual metrics to determine the successfulness of your model. In automated driving, so we know like computer vision or object recognition kind of machine learning model is required for auto driving, but the common off-the-shelf data usually we usually can obtain more training examples on object detection or color and shape detection instead of scenario detection. But for the automatic driving, it's more important if you can recognize a particular traffic scenario. For example, traffic light changing, or for example, the other car that's moving into your lane. That's a particular scenario that's involved in the action with the environment. That's really what we want to recognize. But those training data might not be sufficient to really train model. So we usually rely on the labels that we can easily obtain, like the object recognition. And so, by training a very good shape, color, or object recognition vision model doesn't really imply it can detect the scenario as good. In AI dialogue system, it's similar. So the ultimate goal for a dialogue system is to determine whether this model understands the intent, the real meaning of the dialogue. But it's much challenging to collect the intent label training examples. And it's much easier to collect the word label or sentence label training examples. And for a model relies on those, and we have to be very careful how they can translate to this ultimate goal as understand the intent. Next, I'd like to, so whenever you find the model is not very good, you probably should also ask if your model has been evaluated correctly. Okay, so sometimes it's simply because not the right evaluation metrics is chosen, and so by optimizing this incorrect evaluation metrics, the eventual model learned might not be satisfiable given the real world usage scenario. And here is a case study. So accuracy is probably not always best way to evaluate a model. If, say, we want to build a recognition model to detect the potential malicious personnel in a custom, okay? And so we know that like in the custom, probably 99.999% of the people entering this border is a normal person or benign person. Only very few of them are malicious or terrorists. So it's very likely we randomly pick a person, assign it as not a terrorist, we will obtain 99.999% accuracy. But this kind of model is useless because it never allows you to decide which personnel is a dangerous one. And so for this, in this case, we probably can resort to area under ROC curve, and people are usually use that to evaluate this imbalance scenario. Also, I like to also discuss about if the right evaluation data have been used. So normally training a machine learning model, we divide the data into three parts: the training examples, the validation data, and the testing data. And we want to record the performance on these three sets of data, but we have to be aware that the performance on training data is of course biased because the model already knows the answer. You can try best to overfit the training data. So accuracy actually has to be evaluated on the independent testing data set. And we want to make sure all the features, all the information in the test data are not picked when training the model. Okay, in particular for real-world usage, when we deploy the model online for serving, normally before deploy, we don't know what kind of testing instance will come in for long time serving. So we are not able to pick the testing, even the features in advance. And we use the validation data to adjust the hyperparameters. And because the validation data is very important, it allows us to find a good hyperparameter. How can we pick the validation data becomes the key issues here. And I'd like to show a case study that tells us we have to be aware of the leakage in selecting the validation data sets. So it's one of the competition we have participated. So it's about determining based on the X-ray pictures determine if a person is positive, meaning it contains cancer tissues, or negative, meaning it's healthy. Okay, and eventually we are getting pictures like this one. And each point, like this black dot, is an instance labeled by doctor whether it's positive or negative. Positive meaning that it's a problematic. Negative means it's normal. So it's really a multi-instance classification task, as I introduced previously, because eventually we don't really care about the assignment for each individual black dot, and we care about the assignment for this whole picture. We care about if this particular patient is health or not. Okay, and then but the data comes as a bunch of instances, and if people normally use cross validation, and a lot of off-the-shelf tools like Shou-De Lin, they already implemented this cross validation framework that helps you to divide the data into different portions and use one of them for training and the other for testing. And if by directly employ or directly using those cross-validation functions in the libraries, you will cause a leakage problem because the cross-validation framework actually divides data based on instance level, not on the patient level. And so this will lead to very high training accuracy, but very low testing accuracy, because by randomly divide those training instances, we can pick some of the instances of the testing patients in the training data. So the best way to do validation here is to patient level cross validation. So we have to manually implement this cross validation by divided people into different groups instead of the instances into different groups. So by doing that, we can see that the training accuracy significantly dropped from 90 to 80, but the testing accuracy actually improves. There is a much smaller gap between training and testing, meaning that we are not overfit the data. By the way, so if you want, there is a very nice paper talking about data leakage in KDD 2011, and feel free to check that. So in particular for real world usage, when we need to divide training, validation, and testing on our own, we have to be very aware of to avoid loss leakage. And also one thing people I found that useful, but I don't see too many people doing that, is sampling for representative validation set. So normally people do a random sampling of validation, okay? In particular for real world usage, usually we don't have enough resource to do cross validation. Okay, cross validation, you need a lot of so you need to train multiple times of the model and do evaluation multiple times. Not a lot. Sometimes we don't have the enough resource to do that. We can only try once. In that case, how to pick a validation data set becomes very important. So one way to do that is we can sample, for example, 3 different validation data sets. Okay, and we want to determine which one is the best by implementing several different algorithms. They don't have to be very sophisticated. It can be, for example, a linear regression, a decision tree, and a random forest, for example. So off-the-shelf tools, you can develop several algorithms and try to test those algorithms on the validation data set, okay, and rank which one performs the best using the validation set. And we want a good validation set actually yields similar ranking as the testing set. Okay, so assuming that we don't have the we can assume we have the data on the testing set. We cannot pick the data, but assuming that we know the performance of the testing. So in the real world usage, meaning that we know after deploy this model, what's the accuracy in real world usage. So we can obtain that. Okay, so on the testing and for the competition, it's simply the leaderboard. The leaderboard tells you the testing performance. And we want to pick a validation set whose ranking across different algorithms similar to their ranking on the testing set. This probably implies the distribution of this particular validation is more aligned with the distribution of testing. So the ranking of the algorithm is similar. But don't look at the absolute value of the validation testing because they can be very different. But we really want the consistency in the ranking because we are using this validation set to adjust the hyperparameters. So different hyperparameters will yield different results. So as long as the ranking is correct, we can use validation to find the best hyperparameter, and that's good enough. Okay. So the last question I'd like to answer is if it turns out like your boss tells you like, okay, you need to improve your machine learning model, otherwise you will get fired. And so this the last notice, you need to do that. Then what can you do? And then very likely you need to, if you absolutely need to boost accuracy, then branding and ensemble could be a rescue. Okay. So what this is, I get from a quote from a very famous machine learning winning team. It tells us that every time we add one more model into our ensemble, we have a big jump on the scoreboard. Okay. And so this tells us ensemble, if you do it correctly, is probably useful. And there are two different ideas we can do this combination of models. One is called blending, one is called ensemble. There is subtle difference between these two. Blending means combining the results from probably not a lot of models, a few models. Okay, and using blending, we can resort to nonlinear blending methods like kernel, SVM, or neural network because there are not a lot of models there to be blended. The ensemble refers to combining the results of a lot of models, including blending models or individual models. Usually it takes a lot of models, so to avoid overfitting, we tend to resort to simple linear linear combination or simple voting or average to do ensemble. I will show like two of our previous examples that ensemble actually yes a lot of boost. And in 2011, 2012, Kelly Cup, we are building tens of models, basic models, and first we use blending to combine small set of them, and then we use ensemble to finally integrate all the blending models as well as the individual model. In this case, you need additional validation set in each stage to determine the hyperparameters for combination. So that's a pretty sophisticated process to do this. So that's why I mentioned if it's absolutely needed. Otherwise, ensemble could be very costly, not just computationally, but the whole process takes a lot of time and resources. But there's one interesting sharing to share with you. It's like the ensemble really brings a different mindset to assess the quality of the model. So normally in a competition, or if we focus on single model, we always talk about which model is the best, which model outperform the others, which are not as good as others. But for ensemble, the story is different. The ensemble means we want to combine a lot of models. That doesn't actually imply individual performance is very useful in the combination. So I'll show you an example in our previous competition. So in this example, like we are trying 6 different models, different sets of models, okay? And in this case, this matrix calculation yields the best results. The error is 23.92, outperform the others, okay? And the second best is probably this PPCA, probabilistic PCA model. And this regression model actually performed the worst. So its error is 28, okay? So if we only consider one single model, and we probably throw away this regression model, okay? But now we are trying to combine all of them. And we are trying to learn a good way to assign different weights to combine them. And it turns out like in the very end, this contribution means the weight we learned for each individual model. And the best model, this MF model, obtained the highest weight, which should be reasonable. But this second best model, this PPCA, actually obtained a very, very small weight. Even comparing with the worst model, the regression model is 0.02, and as opposed to 0.0014. So this is because PPCA are optimizing very similar objective as an MF model. So by combining this with MF model, it probably doesn't yield too much improvement in this case. But regression is doing a very different things comparing with the other models. And by adding this into ensemble, it will probably bring us the diversity to the overall solutions, and they will still get a better performance. So that means if you want to consider a combination of different models, a superior model might not be as useful as if it doesn't bring diversity into the model. Also, it also tells us like if you are developing a new machine learning model, it's not necessarily has to outperform all the rest of the pool, as long as it provides benefits for ensemble. By combining this model with everybody else, it brings a boost on the performance. This model can still be useful. Okay, so the final remark. So I believe building machine learning model is very attractive, and partly because there is a clear metric to evaluate the performance. So it's like sports. So we know how well we do right now, and we know if we improve, we'll get better results. And so we get rewards by working harder and harder to improve our model. And so this seems to be a very attractive task to work on. And in this case, we need to understand the definition of success in advance, because it's impossible to keep improving the performance. There's always the upper bound over there. And so what do I mean by understand the success in advance? For some real world applications, we need to first try to evaluate, try to understand whether what's the target, what's the target performance we are looking for. It could be the case that even the best performance any model can do. So there are several ways to estimate that any model can do cannot still fulfill the customer's requirement for the desirable performance. In that case, we probably we probably have to seek for other solutions than a machine learning model. So it's very important in the very beginning, try to understand what should be considered a success. And also another take-home point is that while I'm talking about performance throughout this lecture, but in real world, although performance is very important, but there are two other things we need to consider. One is cost, the other is maintenance for real world usage. Cost means how much efforts the human or the you have to spend on building this model or fine-tuning this model, plus how much computation resource is required for your model to achieve satisfiable performance. So here are two scenarios. You can spend 10 hours tune a 100 DNN model and plus attention, and you obtain 90% accuracy. As opposed to you spend 2 hours, apply a tree-based model, achieve 87% accuracy. Which one is better? Okay, so I'm not telling you the answer which one is better because it depends on the application scenario. If it's predicting, for example, stock price, probably accuracy is very important. You try your best to boost it. But if it's a recommendation, probably you want to face adapting to new world scenario and you don't want to spend too much time and resources to train a model. The second is maintenance. Okay, so once you have built this model, it's not the end of the world. It's not just the end of your job. You need to serve this model to the customer, and then you have to consider how much efforts is needed to maintain this model. Okay, is it too complicated to debug? Is it too sensitive to data or concept drift? Is the parameter the sensitivity of the parameter too sharp that by small tuning it will fail? It will encounter failure. So those are considered as the sustainability and the maintenance efforts of the model, and they can be also important for real world usage. Okay, so I think I will stop here and thank you for coming to this lecture, and I hope all enjoy your life as a machine learning practitioner. And next, I will spend the rest of the time answer questions as much as I can. Let's see. Hey, are there any ways to know whether a domain is transferable? This is a very good question. So as I would say, I wouldn't say there's a rule of thumb that an SOP like you can use to check if a domain is transferable, but easier way is like to check by human knowledge whether telling you the information about this particular domain helps you to determine the label for the other domain. If the human belief is useful, then it's very likely transferable. But if the human doesn't believe to be useful, I'm not saying it's not worth a try, but it's probably less likely to succeed. So it all depends on if doing this transfer learning is cost effective or not. So if you don't, once you have, if you don't have enough label there are several ways you can do. One is to ask people to label your data, and the other is, of course, use semi-supervised or transfer learning. And then in practice, you probably want to evaluate which one is less costly and do that. If there is, for example, there's really nobody can help on labeling, and you have nothing to do, then you anyway have to do transfer, and then you just do it, and regardless of other solution, other options. And also, like, be aware when doing transfer, there is a famous scenario called negative transferring, meaning that adding those data from another domain can lead to negative impact on transfer model, and we have to be very aware of that. How can we know which feature is useful, which technique can be used? And so this is also a big question. And so there's a feature selection techniques over there. So if you don't know, add everything into your model and then feature selection to take over from there, and normally they would select a subset of features that's useful, and which model can be used if you don't know, and try different types of a model. And if you and check the previous slides, I mentioned there are some high level guidance you can use to pick a model. Is that true that people say machine learning is all about feature engineering? It's definitely not all about feature engineering, but feature engineering is one of very key element in boosting your performance. I would say that, but as I mentioned, there are other things you need to be aware of other than feature engineering. But I won't say it's all about, but the feature engineering is definitely a very important step over there. In recent years, the community seeks to move forward end-to-end and reducing feature engineering. What do you think about this? Is this like if you have enough data, end-to-end is always better? And yes or no? It depends on how much. First, end-to-end is very, training end-to-end model is very costly in terms of computation resources, in terms of data required. Okay, so it's not always training end-to-end is the best. Okay, so secondly, it depends on what kind of type of data do you have. If you are training an image recognition model, or like audio recognition, using end-to-end, in particular using deep learning based end-to-end model, could be very useful. But if your data is a tablet data that contains a lot of features, each feature has its own meaning. As opposed to image, those features are simply dots or like grids. But dealing with tablet data, each feature has its own meaning, physical meaning, then feature engineering is useful. Okay, so consider the type of data, type of task, considering the cost. So I wouldn't say end-to-end is always the best solution. Okay. I assume a lot of steps you have described can be automated. Do you know automate search? Yes, so you're right. So right now, a lot of auto ML framework are proposed, okay, to automatically seek for example, feature engineering, but still, auto ML consumes a lot of resources. Okay, once you have to seek for you need to seek for hyperparameter, you seek for different set of features, you seek of different set of feature combinations, you need to seek for different ways to ensemble, and combine all those, it costs a lot of resources to try and error. Okay, so if by using some SOP or some sort of human knowledge to constrain the search space, you will make auto ML much more efficient to find the best solution. So yes or no? Yeah. And for this particular question, auto ML can of course help on some of them, but adding some of the human knowledge into this will make this more efficient. For example, of ordinal encoding or assumption, the distance between easy and median is the same as median to hard. How do you avoid this assumption? Yes, you are right. So it's hard to avoid this assumption. So it's always so it's by try and error. So if you found if your human knowledge believe they are not equally distance, then we should not assign an equally distance. But there are some statistics to help us determine how different are those elements by how frequent they occur together and how they correlated with the labels. And so there are ways to help you determine how to assign those numerical values to the audio features. Will feature perform well in a linear model, can still perform better on other models? Some features may be more suitable for some models. Yes, so of course, so some features, different models, they look for different features to make these decisions. So some feature could be more representative to certain models. And so it's hard to just draw a line telling you which feature is better for which models. And normally we just let the model determine how they were, how much weight they are going to trust this particular feature. Okay. Why testing data distribution is not the same as training data will cause overfitting? Overfitting actually means like you are using the so the testing data, you are using the incorrect features to make decisions. So if your learning model learns that those features are useful to make a decision in your training data, but indeed they are not in the testing data. So if your testing and training are from different distribution, it will lead to overfitting because the training model will incorrectly pick the wrong features and they are not effective during prediction. How to evaluate model with uncertainty in deep learning, for which change random seed GPU, we may get very different results using the same model and data. Maybe in environment is better than maybe. Okay, so I think this question is that, so in deep learning model, there are a lot of parameters in the random seeds. So every time you have difference, those randomness can affect the performance. So when you retrain the model with different initialization or different parameter, the result can be very different. Yes, that's true. And so one way to handle that is, first, like one thing in practice we found useful is to do parameter leveled ensemble. Okay, so if different initialization yields different results, then we can try different initialization for example, 10 times and pick the top 3. And when during prediction, you use this top 3 to do prediction and ensemble on these top 3 parameters. That's one way we can avoid this randomness during training. Changing randomness implies generate different random weights, which cause uncertainty. Okay, I think I have probably answered all the questions here, and we are over time for 15 minutes. I think I'm very happy to be here, and if you have further questions, welcome to contact me. If you are interested in real machine learning model in real life, welcome to join AINTU in the future, and we have a lot of fun things to work out together. Thank you.
Yeah, thank you, Shou-De, for your wonderful talk. Finally, can you give some final suggestions for our students who wants to join industry and become an ML practitioner?
Yes, so as I mentioned, so at this stage, most of students try their best to optimize the performance of a particular model. But I would suggest looking into some other practical issues you might encounter in real world scenario. For example, data are imbalanced. For example, there are missing features. For example, noise in the labels. For example, model is not unstable, is not stable when dealing with concept drift. Those will be very useful when you enter industry facing real world ML challenges. So as long as as early as you can study those problems, they will be better. You will be better equipped to deal with the real world problem in machine learning. Thank you.
Right. Thank you very much. So we'll finish this lecture here. Yep. Thank you everyone for joining. Yep. See you. Bye bye.